Hello everyone, this is going to be the second video on context-free languages. In the previous video we introduced context-free languages in the Chomsky hierarchy. After regular languages, context-free languages is the second level in the hierarchy. So every regular language is also a context-free language, but not all context-free languages are going to be regular. We informally define context-free languages to be those languages that we can represent them using a context-free grammar. And basically, if you think about the intuition of the context-free grammars, the idea is that all those languages that you can find some recursive structure to generate the strings in them, they are going to be a part of context-free languages. There are plenty of applications for context-free languages, all programming languages, markup languages, everywhere that we kind of define some artificial grammar and language, not the natural languages, they're going to be context-free languages. We discuss about the formal definition of context-free grammars. Any context-free grammar can be represented using a for tuple, a set of variables, a set of terminals. The set of variables and terminals should be disjoint. You cannot have a token which is both terminal and non-terminal. And a set of rules. The rules will be represented using, this format, that the left-hand side should be a single variable, a single non-terminal, and the right-hand side can be any sequence of terminal and non-terminals. And there is a starting symbol that any string that you generate using this grammar should start from the starting symbol, and by following a set of rules, you can generate a string in your language. We have talked about the parse tree, about derivation, recursive inference, and this fact that all of these are different representation of how a grammar works and how, in fact, how a grammar generates a string. So for each string in one language, which is a context-free language, there is at least one parse tree, and there is an equivalent derivation for that, and there is an equivalent recursive inference for that. We have talked about the leftmost and rightmost derivations, that when you are generating a string, if you in your derivation, if you always stick to the leftmost variable and expand always the leftmost variable, it's going to be leftmost derivation. If you stick to the rightmost, expanding the rightmost variable in the derivation, it's going to be rightmost derivation. And all of these, parse tree, leftmost derivation, rightmost derivation, recursive inference, are equivalent. All of them just representing how a grammar generates a string. So in this video, I'm going to talk about ambiguity in context-free grammars. Let's see an example. I have a grammar and I have a string that can be generated by that grammar. Let's write the derivation for that. So, and I'm trying to actually write the leftmost derivation here. S goes to AS, then I take A. This is the leftmost derivation. I am going to use the second rule for A. Then I am going to use the first rule for A. And then I am going to use the last rule for A. And then use the second rule of S to get rid of S. Oh, sorry. I missed one here. This is a leftmost derivation, right? Because always I stick to the leftmost variable to expand. Okay, now I'm going to show you something else. Another derivation from S, go to AS. Then again, I'm going to stick to the first, the leftmost variable to expand. But this time, I am going to use the first rule for A first. Then use the second rule, 0, A, 1, 1. And then the last one. And then, right? If you look at this, you can see that again, I always stick to expanding the leftmost variable. What does this mean? It is telling me that I have a string using that in the grammar that can be generated by this grammar, that it has two leftmost derivations. Both of them are leftmost derivations. It has two leftmost derivations. Both of them are valid derivation. What does this mean? Remember, we had a question last week. I don't have a slide to show you here, but it was asking that is it possible for some strings to have more than one leftmost derivation? And the answer was yes, depending on the language. It is telling me something. If you have more than one leftmost derivation, if the leftmost derivation is not unique, it means that there are completely two different ways to generate the string. And because of this fact that we know the equivalency of leftmost derivation, rightmost derivations, and parse trees, it tells me that if there are two leftmost derivations, it means that there are two different parse trees. So let's try to draw the parse trees for these two different derivations, and you will see that they are going to be different. So the parse tree for the first one, maybe use the color black. It's going to be, the first one has two branches, A, S, then A goes to 0, A, 1. You see that I'm exactly following the rules here. And then it is going to 1, A, and then this one goes to oh no, I made a mistake here. It was like this 1A, right? And then this one goes to 0, 1, and then this one goes to epsilon. And so what is the string that you read from this parse tree? It's just like you read all of the leaf nodes. It's going to be 0, 0, 1, 1, 1. We don't write the epsilon, right? So let's look at the parse tree for the parse tree equivalent to this leftmost derivation. S goes to AS, AS goes to A1, this is going to 0, A1, and this one goes to 0, 1. It is again resulting exactly the same string. I forgot to finish the parse 3. This is going to epsilon. And the string here is going to be again 0, 0, 1, 1, 1. Now you can see that these two trees are completely different. So when we have a grammar that there is at least one string generated by that grammar, which has more than 2 parse trees, we call it ambiguous. So it doesn't matter if you find a string that has more than 2 parse tree, or a string that has more than 2 leftmost derivation, or a string with more than 2 rightmost derivation. All of them are going to be equivalent, right? And this ambiguity is going to be a property for the grammar. Sometimes the language is not ambiguous itself, but the grammar that you write for it is going to be ambiguous. Exactly like the way that we write the regular expressions for the regular languages, that the language was unique, but it is possible to write down different regular expression for that. Also, in the context-free languages, for one language you can write down different grammars. So sometimes the language itself is not ambiguous, but the grammar that some specific grammar that you wrote for it is ambiguous, and you can write down an unambiguous grammar for that. But sometimes the language itself is ambiguous, and we call it inherently ambiguous, and we cannot write down a grammar, unambiguous grammar for that. So I have talked about this concept of ambiguity a lot, but I didn't tell you that why we care about ambiguity. And in fact, you should know that ambiguity is not good. We try to avoid ambiguity always. But what is the reason? I'm going to show you with another example. That's why we care about the parse trees and why we care about the ambiguity. Is it good to have more than one parse tree for a string, or it is bad? And why the ambiguity is bad, why I'm saying the ambiguity is bad. Look at this string here. And I'm going to again write down some derivation for this one. Okay, I wanted to write a leftmost derivation from E. I can go to E plus E. Then I can, this is going to be a leftmost derivation, right? I'm going to stick to the leftmost variable. So E goes to be able to generate this, I should expand this one in this way, right? Still stick to the leftmost derivation. E goes to A. Then I'm going to use to replace this one with B. And replace the last one. Let's see. This is one leftmost derivation. Another leftmost derivation. E goes to E multiplied by E. Then the first E goes to A. Then I'm going to replace the second. This is the last, the only variable. I need to replace it using the first rule. Then replacing E with B. Then replacing the last E with C. These are two different leftmost derivation, and equivalent to each one there is a parse tree. So what is the parse tree for this one? E goes to E plus E, E multiplied by E, this one goes to A, this one goes to B, and this one goes to C. And the leftmost derivation for the second one, E multiplied by E, E go to A, E plus E, this is going to B, and this is going to C. So it is very clear here that the parse series looks completely different, right? And so why this is important for me that the parse series are different? Because the parse series, as I remember this slide from previous that I told you, that when, for example, you are writing a compiler, the parse series not only just check the syntactic correction, the proper syntax, to make sure there is no syntax error, but also parse series are going to give us some interpretation from the program, because it gives us some understanding from the program. Here, these two parse series that we draw are going to tell us something. When you have this tree, when you are going to calculate the expression, you are going to calculate it using the parse tree. This is a tree that tells me that when you are going to evaluate the expression, the main expression here, you are going to use this parse tree. So, for example, just assume that whatever here you have is going to be the result of these two, and then get the summation between them. What is the value here in your parse series is going to tell you that multiply whatever you have here to whatever you have here, and then send back the result. So it's going to be A multiplied by B, and then add it to C at the end. So if I'm writing it using parentheses, is going to be something like this, that you first multiply A to B and then add C to that. What the compiler or any parser will understand from this tree, it understands that you have to first evaluate the corresponding expression here, which is going to be B plus C, and then get the result, multiply it to A. So here we understand A multiplied by B plus C from this parse tree. So now you understand that why ambiguity is bad, because parse tree not only is checking that how the string has been generated, it is in fact gives us some interpretation for the expression. So when you write something like this, you don't want to have two different definitions for your expression. You want it to always have a unique expression, unique interpretation for that. Always for us, this is going to understand as first multiply A to B plus C. This is a rule for humans, that we always know that we give the higher precedence to the multiplication than the addition. This is a rule for us. But anyway, this is something that we want to a computer understand. If I'm writing some arithmetic expression in my program, I want my computer to understand it in this way, not this one. Right? Not only understand it in this way, always understand it in this way. If your grammar is ambiguous, if you write a grammar which is ambiguous, and the parser will try to actually parse it using the ambiguous grammar, it can actually end up to this parse tree or this parse tree, and based on the result that it gets, it can get different results. So we wanted to write grammars that doesn't have ambiguity, and for every single string you have a unique parse tree. So you have a unique interpretation for your expression. So we want to actually try to see that is it possible to write an unambiguous grammar for this language. Remember I said that some languages are inherently ambiguous. For those languages you cannot write down a non-ambiguous grammar, but many languages are unambiguous. Okay, so for example, the language for this grammar that we wrote, this simple language that we defined for arithmetic expression, is not inherently ambiguous. I can write down an unambiguous grammar for that, and I'm trying to rewrite another grammar which is unambiguous. How we can do it? Unfortunately, there is no algorithm that I can give you to write an unambiguous grammar. This is a problem that for every language or every grammar that you see, if you find it ambiguous and you want to write down another unambiguous grammar for that, this is just a new problem. You have to solve it. But there are some specific approaches that you can use to write down an unambiguous grammar. The one that I'm going to use here is I'm trying to use more variables so that by giving some definition to each variable, I try to avoid some specific action or some specific derivations. How I'm going to define, instead of just having one variable in my grammar that generates everything, I am going to define 4 different variables. One variable which is just responsible for generating the identifiers. Okay, this variable I, it only is going to generate the identifiers, and these are the rules for that. And I have actually simplified based on the grammar that I have. You can see that the identifiers, the constants, the identifiers are going to be only A, B, or C. This is very simplified actually language. Or the only 2 integer numbers 0 and 1. So I can be only translated to this, nothing else. I am going to add 3 more variables. One variable f, and that the purpose of this variable is to make sure that if you have a variable f, this f can only go to an identifier, or it can actually generate a new expression surrounded by open and close parentheses. Okay, so we are going to represent it in this way. This is telling me that if I reach to f, I cannot expand f and split it using multiplication and addition. If you look at the previous, the example that we had to showing that the grammar is ambiguous, is that the issue is that I have 2 rules. I have just one variable, and that variable can be splitted by addition, can be splitted by multiplication, can also go to the identifiers and constants as well. This is actually the source of the reason why it is ambiguous. When I see something like A multiplied by B plus C, I can start it by generating this part first, this one and this one, or generating this one and this one, right? I'm allowing to split in 2 different ways. By defining different variables and giving different responsibilities, different jobs for them, I am avoiding that. Okay, so the other variable that I have is t, that this one is responsible. You can actually use this one to split based on multiplication, not plus. So you can see that this is going to t goes to t multiplied by f. So this is the recursive part of it. It allows you to actually just repeatedly have different multiplication. For example, a multiplied by a multiplied by a. Something like this can be, this is a recursive structure, right? You can actually just do it using this rule, that this part of it is the recursion is going to happen here. And the other part of it, you can see that I didn't put t here. I didn't write it as t multiplied by t because I don't want to give ways to split it into different, I don't want to allow the ambiguity here. If you write it as t goes to t multiplied by t, some strings like this are going to have more than 2 parse trees because you can split it from, you can split it here or you can split it here, right? By forcing the second part to go to f, I'm forcing that always, if you have more than one multiplication, you always actually split from the, you always go with this one. So this one will actually be t and this one will be f. Okay, or t can directly go to f. If you don't have any multiplication to split, t directly go to f. And the last variable, or basically it's going to be the starting variable, is e, that this one is responsible to split the variable based on plus. Okay, and then again I'm doing the same thing. I allow the recursion on one side of it, always from the actually left of it, right? And I didn't write something like e goes to e plus e, again to avoid ambiguity for the cases like a plus a plus a. So always if it has ambiguity, it has more than one plus, it always split it from the end. The last part is going to considered as t, and or if you don't have plus, for example, you have a string that only has multiplication or something like that, you can directly go to f. Sorry, to t. So now let's get back to the last example that the previous example that we see, and see that how we can derive, how we can write a parse tree for this string using this grammar. I definitely need to start from the starting variable, and you can see that if I am going to generate plus, I have to apply it here. I have to split it here. This is going to be e plus t. I cannot use any other rule here. This is the only rule that I can use. And then e here can go to t directly. I'm trying to kind of simulate the leftmost derivation. Then t can be expanded using this rule. I have a multiplication. I have to actually use this rule to generate that. So this is going to be t multiply f, right? And then what t goes here, we can see that I don't have any other operator. For me, I have to actually generate a. How to generate a? T should go to f. F, I don't have any parentheses, so I'm not going to use this rule. This is going to go to the other variable I. And this one is going to the constant, the identifier a, right? Then f. Again, f here needs to be converted to I. You cannot use any other rule. And I will be converted to b. Then t, again. So t can go to a rule like this, but I don't have any multiplication remain to be generated. So that's it. It has to go to f. And from f, we don't have any parentheses, so I have to use this rule. it has to go to I, and from I it goes to C. So this is a parse tree, and this is the unique parse tree that you can generate for this string. And how we understand this, how we interpret the expression, you can see that this is understanding it as exactly first multiply A to B from this side, then get the result added to C. So it will just interpret it in this way. There's no other way. So just as an example, try to play with this grammar, write down the derivation for some other examples. For example, a good example here is going to be something like A multiplied by B multiplied by C, something like that. Although the result here, if you have two different parse trees, the final result is going to be the same, but we don't want to have ambiguity in our grammar and different ways to interpret it. We are going to always stick to just one unique parse tree. And let me actually show you the parse tree for this one. E goes to, you don't have any plus, so basically I'm not going to use this part of it. It directly goes to T. From T, it can actually go to T multiplied by F, and again from T it needs to actually generated another multiplication, right? So it needs to go to T multiplied by F, T goes to F, F goes to I goes to A, F here goes to I goes to B, F here goes to I, and I goes to C. Right, and it's not possible to draw any other parse tree for this expression. Try it for different examples. For example, A plus B in parentheses multiplied by C. Draw the parse tree for this expression. So, for example, A multiplied by B multiplied by C. Sorry, plus instead of multiply, and multiply by something, for example, another A at the end. Do it over different examples and see that the grammar perfectly avoids the disambiguity. Not only it avoids the disambiguity, it gives the higher precedence to multiplication over plus. Why? Because in fact, when you are splitting E, by forcing that E can only split over addition or plus, it is forcing to have plus higher in your parse tree. So when you have, for example, a multiplication and plus both of them, you have to use this rule first. You cannot use a rule to split this part in this way, right? Because of this, because of forcing E to split it based on only plus, you are forcing plus to appear higher in your parse tree. So when it appears higher in the parse tree, it is going to be applied later. So multiplication will be appear lower in your tree. So it means that when you are calculating the corresponding expression, you have to calculate multiplication first. You are giving higher precedence to the multiplication over plus. If I change these two rules, so a split based on multiplication in T and a split based on plus here, I'm giving higher precedence to the plus, to the addition over multiplication, and it is not good. This is one thing. The other thing that appears in this grammar is that we are also implementing the associativity rule, that if you have two operators that both of them have the same precedence, you are giving the higher precedence to the leftmost. So if you have something like A multiplied by B multiplied by C, I wanted to first multiply A to B, then multiply the result to C. This is the associativity rule, and we are, normally in computer science we have the left associativity. It means that you are going to the higher precedence to the leftmost derivation, to the left operator. You are applying it from the left to right. And because I am forcing the recursion here on the left side, I'm giving the higher precedence. I'm actually implementing this left, the left associativity. Why? You can see that this A, B, C will be A multiplied by B multiplied by C will be interpreted as first A multiplied by B, then get the result and multiply it to C here. Okay? So it is forcing you that always actually do the recursion on the left of it. So the leftmost operator will appear lower in your parse tree. So we have, I'm going to actually just give you more examples on the ambiguous grammars later, but just again, this reminder that some context-free languages are inherently ambiguous. It means that it's not possible to write an unambiguous grammar for them. And here is an example. Look at this example. This is an interesting example. It is telling me that you have the alphabet has A, B, C, D, and the number of these characters are, you have a couple of A's, a couple of B's, a couple of C's, followed by some D. So either the number of A and B's are equal and the number of C and D are equal. For example, like A, B, C, C, D, D. Or the number of A and D are equal and the number of B and C's are equal. Okay, these two strings are in the language. So how can, is it even a context-free language? Yes, it is a context-free language because I can write down this context-free grammar for this language, that S goes to, basically if you think about it, it is the union of two different sets, and I'm going to write down some grammar for each one. S goes to, for example, either A or B. Then A is responsible to generate the strings that has in this format. So the number of A and B's are equal, followed by some C and D, which the number of C and D are equal as well. So this is going to generate for example, let's use CD, where C goes to A, C, B, or epsilon, and D goes to C, D, D, or epsilon. Okay, and I can write down some other rules also for B. B is responsible to generate the strings with this property, that so it is going to generate like A, B, B, or it goes to, A, B, D. I'm going to generate equal number of A and D's, right, as much as possible as I want, and then it can go to, for example, some other variable like F, and F is responsible to actually generate equal number of B and C for me, B, F, C, or epsilon. Okay, I don't know if it's clear here or not, but this is the full grammar that I wrote. I basically consider it as two different sets, the union of two sets, and write down the grammar for each one. And by using this rule, it's just like I'm generating both, all the strings in both sets. So this is exactly showing you that it is this string is the union of this language is the union of these two languages, and I can write down some grammar for each one, but this grammar is definitely ambiguous, this grammar that I wrote. And the reason is that I can prove that this grammar is inherently ambiguous. This language, is inherently ambiguous. And the reason is that some strings like this, that the number of A, B, C, and D, all of them are equal, can be generated both in this set and in this set. So for my grammar, the grammar that I wrote, they can be generated either using A or B. And because of that, this language is inherently ambiguous. You cannot write any grammar, unambiguous grammar for this, because whatever you do, the only way to write down a grammar for that is by writing, split it to two sets and write one, a grammar for this one and a grammar for this one. And those grammars, you cannot force them to, doesn't generate a string like this, because this string belongs to both sets and it will be generated by the grammars for each set. So another interesting point that we learned here is that context-free languages are closed on their union. Why? I basically roughly actually prove it here, that if you have two sets that both of them are context-free language, it means that you can write down a grammar for each one, context-free language for each one, context-free grammar for each one. And then by, for example, if the starting variable for the first one is A, the starting variable for the second one is B, I can create a new grammar by getting the union of all those rules and adding one more rule and one new starting variable S that goes to A or B. So that's it. I can write down a grammar for the union of two other context-free grammars using the grammars that I wrote for each one. So let's see some more examples. So far I have, the approach that I have already used in this example to be able to write an unambiguous grammar was this approach. I tried to give some semantic meaning to each variable and define different variables for different purposes. So in this way, I'm avoiding the ambiguity in the grammar. The other way is that if you started thinking about your program in recursive way and define different recursive rules for each part which is recursive, you can also get a good approach for write an unambiguous grammar. But in general, I can say that there is no algorithm to write down an unambiguous grammar for a language, unfortunately. But for any new language, this is going to be a new problem that we have to solve it. So let's see another example. We have this language, which is a set of all binary strings that has equal number of zeros and ones. I'm going to write down a grammar for this, which is unambiguous. If you write down an ambiguous grammar for this, it's going to be easy. I mean, there are many different ways to write a grammar for this language. Many of them are ambiguous. For example, if I say S goes to like 0, S1, or 1, S0, or you can see that I'm just forcing that whenever you are generating a 0, you are generating a 1 as well. These are going to be only the nested actually lines, and also SS and epsilon. This is going to be ambiguous. So let's look at a string like 00110011. S goes to 0, S1, then S goes to 1, 0, S and 1, and again S here goes to 1, S0, 1, S0, and epsilon. This is going to give me this string, right? And I can find another parse tree as well for that, like this. S goes to SS, 0, S1, 0, S1, and epsilon. This one goes to 0, S1, 0, S1, and epsilon. This is also give me exactly the same string, right? If you read from here, 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 and here. There are two parse trees, and that's enough to prove that this grammar is ambiguous. So let's try to write an unambiguous grammar for this language. The issue with this grammar is that we are using a single variable which is responsible to do everything. With the first rule, it tells you that, okay, whenever you you generate a 0 and start with a 0, later on don't forget to add a 1. And this one allows you to generate ones first instead of zeros, but at the end you are generating a 0. It's forcing you to generate a 0 also. And this part is just a concatenation to have all possible orders, not only the the nested formats, but all the combinations, including by concatenation. It gives you more power, so you can generate all possibles. So I'm going to rewrite this grammar, actually try to define more variables and refine this grammar. What I am going to do is that, let me actually just show you the grammar. I have defined two more variables here, A and B. And instead of, unlike this grammar, that whenever I generate a 0, I forced it to generate a 1 after that. Or if I generate a 1, I force it to have a 0 later. which actually causes ambiguity because you don't know that these ones or zeros are associated to which variable. I'm going to fix that association here. So whenever you started with a 0, okay, so you are saying that you owe me a 1 later, actually. Okay, so I am adding a variable, another variable that I'm calling it a. So a basically just tells me that you have you need one more. You need to generate one additional one. This is the meaning of the variable a. And similar to that, if I generate actually a 1, I put a variable b associated to that. I'm not generating another 0 directly, but I'm putting a variable b, which means that you have to generate one more in this variable b. Okay? And I am actually covering this concatenation, basically combining all these rules, all these 3 rules, and write just 2 rules. Put s after both of the rules. And also by having actually epsilon at the end, I am covering everything. So now let's look at the rules for a and b. The rules for a and b is that, okay, a tells me that you need at least, you need one more, okay? So it can directly just convert it to 1 and you are done. Or if you wanted to have, repeated number of zeros, that's okay. So you can say that, okay, generate a 0, but if you generate a 0 from a, it means that no, you are 2 ones short. You have to generate 2 ones more. Okay, I can define another variable here, or instead of that, reusing the variable a and write the rest of the rule as AA. Exactly the similar logic for b, that b is supposed to generate a string that the number of zeros is exactly one more than the number of ones. So it can directly just generate a 0 and done. Or if you wanted to have a sequence of ones, you can say that, okay, that's fine. After you have generated the 1 there, you can still generate 1. You should be able to generate all possible orders of 0 and 1s, right? It is just about the number of 0 and 1s that we care, not the order. So you can generate a sequence of 1s, but if you do that, it means if you generate a sequence of 1s, another one using b, it means you are owing me 2 more zeros, right? So I am actually writing it by a double b at the end. So if now we try to write down a parse tree for the previous example that we had. This was the example, right? Now let's see that what the parse tree would look like. Because I have a 0, this is forcing me to use the first rule, 0 a s. And a needs to actually be expanded now. I have another 0, so I have to use this rule, 0 a. Now I have to expand a again. You see that I need to generate a 1, so I am going to use the first rule. A goes to 1. And this a needs to go to 1 as well because I need to generate another 1. There is no other, you cannot use this rule, right? Because it's generating a 0. And then s needs to be expanded again. I have to generate a 0. It means that s has to use the first rule, 0 a s. Exactly similar to the first part. From a you need to get a 0, so the second part of the rule needs to be used, 0 a. Then this one needs to go to 1, this one needs to go to and s goes to epsilon, and that's it. There's no other way to draw a parse tree for this string using this grammar. The grammar is unambiguous, and we can actually prove that this is unambiguous, a formal proof, but I'm skipping that proof here. Okay, let's look at another example. What do you think about this grammar? S goes to SAB or epsilon, A goes to 0 SA, B goes to 1 SA. Try to actually write a derivation for this string. In fact, if you think about the grammar has some, I mean, the recursive part of it is appearing here and here. And then when it actually goes to terminals, whenever it generates a 0, it is forced to generate a 1 as well. Or whenever it generates a 1, it is forced to generate a 0 as well. So again, this grammar exactly represents the same language as we had in the previous example, equal number of zeros and ones. Let's draw the derivation tree for this example that we had. S goes to SAB, then AB can actually go to 0. I mean, it is clear that this is ambiguous, right? I just actually wanted to show you that this is ambiguous, but I think it is clear that this is ambiguous. Even using a shorter example, you can understand this is going to be ambiguous. A simple string like 0, 1 even can have two different parses. Let's actually just try it over this one because this one is going to take some time. I just wanted to make it shorter. So S1, this one goes to epsilon, this one goes to epsilon as well. And then this one goes to epsilon. Or you can have another parse tree for that S goes to SAB again, then S goes to SAB again, then S go to epsilon, then A go to 0 S1, epsilon, 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 and epsilon. Okay, it is very clear that even for a very short string like this, you can have two different parse trees, and this is the grammar for the same language, the equal number of 0 and 1s, and it is ambiguous. Let's see another example. We wanted to write a context-free grammar for this language, that a number of zeros followed by exactly the same number of ones followed by exactly the same number of zeros. What do you think about this problem? How we can write down a context-free grammar for this? If you think about this problem, you can see that it's not possible to write a context-free grammar for this language. Yes, there are some languages which are not context-free. We cannot write down a context-free grammar for this. This is something that it's going to be easier for me to show it to you. It is not context-free when we have talked about the push-down automata, the recognizer, the machine for the context-free grammars. But in fact, the intuition here is that 0-1 part can be generated using some recursive structure. But you cannot, by forcing your grammar to be context-free, it means that the left-hand side should only have one variable. You cannot force it to generate the equal number of zeros followed by that. This part can be actually generated, right? But you cannot count that how many 0, 1 you have generated so that you can actually generate the equal number of zeros later. Okay, so because context-free grammars or this specific have this specific format, the left hand side should be a single variable. You cannot write a recursive structure using context-free grammars for this language. How about this one? This is going to be a couple of zeros followed by equal number of ones followed by a couple of zeros, that there is no relationship between these numbers except that these two are going to be equal. If you think about this, this is easy to write a grammar for this. I can think of it as a concatenation. You have a string which we know that this is context free. Right, I can write down a grammar for that, and I can actually create another variable which is responsible to generate this part. So a grammar for this one can be written as A B, where A goes to A is supposed to actually generate the first part. So 0, A, 1, or it can actually go to epsilon, and B goes to just actually generated some zeros, 0, B, or epsilon. Okay, that's it. This is going to be a grammar for this language. One nice thing about this example is that we have learned one more property about the context-free grammars or context-free languages. Context-free languages are closed under concatenation. So if you have two sets that both of them are context-free, it means that you can write a context-free grammar for each one. And you can, so for example, this one is a grammar for the first part. This is the grammar for the second part. I just added one more rule, that S goes to the starting variable of the first language and B is the starting variable of the second language. So this way, this is even actually a proof that the context-free languages are closed under concatenation. But let's actually look at another example. Just when we are talking about the closure properties, I'm going to just show you another interesting thing. That look at this string. This string is just the reverse of this one, right? You have this part which is not the reverse of that, but conceptually reverse. You have a couple of zeros, then followed by this string which we know that this is context-free, right? And this is also context-free grammar. I can write down a context-free grammar for this language simply, because we know it is closed under concatenation. But by actually comparing, by looking at this example and the previous one, and L1 and L2, you can see that if I take the intersection between these two sets, I will reach to this example. That I already know that this is not going to be context-free language. I cannot write down a context-free grammar for that. So this is also telling me that, unfortunately, context-free grammars, context-free languages are not closed under intersection. Another point that we can conclude here is that they are not going to be closed on their complement, and they are not going to be closed on their set difference as well. I mean, only from this one and using the set rules, we can conclude this one and this one both. By knowing that the context-free languages are closed on their union, but they are not closed on their intersection. So we can conclude that they are not closed on their complement, and they are not going to be closed on their set difference as well. Let's see another example. We wanted to write a context-free grammar for this language. This language, if you think about it, this is a regular language, right? Because what I wrote actually is a regular expression. This is a regular language. all regular languages are context-free. So we should be able to write a context-free grammar for this. And it's going to be easy. I would write a grammar like this, that S goes to A and B. A is responsible to generate the zeros, and B is responsible to generate the ones. So now I'm going to actually just write something more interesting. I wanted to write a context-free grammar for the complement of this language. Complement of this language. What does that mean? It means that all the binary string that doesn't have any all the binary string which are not in this form, a couple of zeros followed by a couple of ones. It doesn't have, the string is not in this form. How can I write this one? First thing, this is context-free language, right? Because it is regular language first. So we should be able to write a context-free grammar for this one as well. And the reason is that this is regular, the complement of that is regular, so the complement of that is context-free grammar as well. But it is a little bit tricky to think about this problem, the complement of it, all the strings, binary strings which are not in this form. Instead of directly thinking about how to generate these strings, I can think about it in the different approach. I wanted to actually just take it this approach, that I will split all the strings in this set, in this language, to 3 different sets. The set of all strings that are just zeros, the set of all strings that which are just 1, and the set of all binary strings that contains the pattern 1, 0. And the union of these 3 is going to be exactly equal to the language that I am actually looking for. If you think about it, it is going to cover everything. Just ones, just zeros, just ones, or whatever you can be, just have this pattern. If it does have this pattern, it's going to actually just force it to not be in this format. That's enough. So now it is easier to solve it. I can write down a grammar for this set, I can write down a grammar for this set, and I can write a grammar for this set and get the union of all the sets. And this is going to be the grammar. So as this part A and D is going to generate this part for me. A goes to D, this pattern 1, 0, and D. So it's forcing that if you go to A, you have to generate 1, 0, this pattern 1, 0. And then the rest of it, how about D? D can generate any string, any binary string in any format. So it's just like I'm allowing it to have any format that it wants. Just generate as many number of zeros and ones as you want. I forced to have that pattern here. Or you can, from S, you can go to B, that specifically just generate zeros, or you can go to C, that specifically just generate ones. Right? And that's it. This is going to be the grammar for this language. Let's see another example. What do you think about this language? This grammar? What is going to be the language of this grammar? If you think about S, you can see that S goes to a concatenation of 3 variables. Now I have to actually look at each one and see that what each one will generate. The variable A will never go back to S. It actually just repeatedly generate A, or will disappear at some point. The variable B just repeatedly generate little b's, and the variable C generate little c's. So basically, if you think about the combination of all this is going to be a couple of A's, and you see that there is no restriction on the number of them. So a couple of A's followed by a couple of B's and followed by a couple of C's. This is going to be the language of this grammar. And as you can see, it is a regular language again. One thing that I wanted to actually now introduce is that because regular languages are context-free language, regular languages are context-free language as well, it is possible to write a grammar for them, right? But not only it's possible to write a grammar for them, we can actually define a specific form of context-free language, context-free grammars for them, which is called regular grammars. If we have a regular language, we can write down a context-free grammar for that, which is in the form of a regular grammar. What is a regular grammar? So a context-free grammar is regular if each rule is in this specific format that I wrote here. Either any of these three formats. Either A, each variable goes to a set of terminals. W is just a set of terminals, a string of 0 or more number of terminals. You cannot have variable in W. Or it can go to WB, where, as you can see, W again is the same. It is going to be a sequence of terminals, and you can only have one variable at the end of it. Or A can actually go to epsilon. It can be actually covered with this rule as well, but anyway, I wrote it to be more explicit. So this is going to be, we call this type of actually grammars right linear, and the reason is that that variable, that single variable which is allowed on the right hand side, comes at the rightmost of the string. If you write your rules to be in this form, this is going to be left linear, but you should be either right linear or left linear. You cannot have a combination of that. If your grammar cannot have both these two formats, both these two rules. Either you have to stick to right linear or you have to stick to the left linear. Okay? And one theorem here is that, I don't want to actually just prove it, but the theorem is that if you can write a regular grammar for a language, it means that that language is regular. And if a language is regular, you can write down a context-free grammar for that, which is a regular grammar. You can prove it. I mean, I'm going to leave this one as an exercise for you, but the proof is available at the end of the slide. So go, whenever you write it down, to just check your answer, go and read the full proof at the end of the slides. So now that we know about the right linear grammars, I wanted to actually just go back and rewrite a right linear grammar for this language. You can see that this is not a regular grammar, right? Because I have a rule like S that goes to ABC, more than one variable at the more than one variable on the right hand side of the rule. These are actually the correct format, but this one is wrong. I have to actually fix that. So how can I fix that? I can just replace this rule with a couple of actually more rules, that S goes to A, or it can go to B, or it can go to CC. And then A can go to AA, or as you can see, I'm not actually repeating S in this structure. So I'm repeating all the rules here. I have to repeat them so that this variable is supposed to generate a couple of zeros, and whenever it moves to B, it is done. It has to start a generated B's or just generate C. Or it just can skip the B's and started generating C. But if, for example, it goes to C, it will only generate C. This is going to be a valid regular language for this, regular grammar for this language, and you can see that it generates the language and it is regular as well. All the rules are right linear. You have only one variable, at most one variable on the right hand side, and it is coming at the rightmost of the right hand side. So one interesting thing here is that, about this theorem and the proof that I told you, how to prove it. In fact, we should be able to say that if I have a regular language, it means that there is going to be a finite state for that. So if I can convert the finite states to a grammar, if I can find an algorithm to convert any finite state to a regular grammar, this is going to be one part of the proof, that you prove one side of it. And if you can convert any regular grammar to a finite state, you are proving the other side of it, right? So these exercises are going to help a lot. The first exercise is that I have some finite automata. I'm going to convert them to regular grammars. How to convert them to regular grammars? The idea here is that over in all these actually DFAs, I can say that, okay, for this state A, I can start writing a variable and say that, okay, from A, then just follow the transitions. The transition over 0 tell me to just go to the variable A again. So instead of this transition, I can write a rule, right, in this way, that it actually repeatedly use A and go over that. It generates A and repeat over A. Generates 0 and repeat over A. And for the next transition, which is over 1, I'm going to write another rule that tells me that over 1, it goes to another variable B. And similar to that, I'm going to write, add a variable with a couple of rules for this state B. Again, state B over the transition 1, it stays, so I can write it in this way. And over the transition of 0, it can go to the state C. State C have two transitions. Again, over 0, it stays at a state C, and over 1, it stays at a state C as well. But the thing here is that so far everything is good, right? I can, basically, I have converted all the transitions in my finite automata to some rule, which all of them are valid regular format. As you can see, all of them are left linear, right? I only have at most one variable and it is coming at the end. But when you are generating a string, when you should stop at somewhere, right? Starting from A, you should stop. When you are stopping, in fact, in your finite automata, when you reach to C, you can stop, right? So I need to add one more rule that C can disappear. So C goes to epsilon, which means that C is an accepting state, right? So let's write the regular grammar for this finite state. I'm going to exactly follow the same schema that starts from A, and A goes to, it has a transition over 0 that goes to A, and it has a transition over 1 that goes to B. For B, again, I have a transition over B that goes to B, and a transition over 0 that goes to C. Then C can have a transition that go to over 1 that goes to B, and has a transition over 0 that goes to A, right? And because this is final state, it can actually disappear as well. That's it. It is going to be a valid right linear grammar for this finite automata. And the last exercise is that we wanted to draw an automaton for this language, for this grammar. This is a valid regular grammar, right? This is all right linear. All the examples have all the rules on the right hand side have at most one variable, and all of the variables are coming at the end. So how to convert this one to a finite automata? This is a little bit more sophisticated than the previous. I mean, the converting automata to regular. I am going to start with a state that let's just give it the name of A, because A is your starting variable, right? And from A, I'm going to just do the reverse of whatever I did here. That converting the transition to the rule, here I'm going to convert the rules to transition. But one thing that make it more complicated is that some rules, like this one, has more than one token terminal, right? I cannot write a transition of 0, 1. So if you have more than one terminal, you can add some dummy variables. So from A, using a 0 over 0, it goes to this dummy variable, and from this variable it goes to, with the transition of 1, it goes to another variable that let's give it the name B. It is associated with that variable B in the grammar. Or it can directly go to C. How to represent this? You can see that it's just like you don't have a token here, right? Before C. You don't have a transition. Or you can think of it as a, yes, I have a transition, and that transition is epsilon transition. So I can write it as an epsilon transition. And you see that converting the regular grammar to the finite automata is converting it to an epsilon NFA. It is not going to be DFA. Later on, you can simplify it and convert it back to DFA. But that's fine to just, we are just trying to create an automata. It doesn't matter if it is finite state or it is, if it is deterministic or non-deterministic. So let's just continue and finish all the, the transition for the rest of the variables or states. The variable B has three rules. One transition of one rule that has 1, 1B. So again here I need another dummy variable, which from that it's coming back to B as well. Okay, I didn't give any name for them. You can give any name that you want. And from B you can also go to C with the transition of 0, or you can go to A with transition 1. And now for C, you can either go to A with transition 1, or you can go to 0, or you can go to 1. What does this mean? It means that you are not going to, C is disappearing by, C is replacing by 1 or 0. So it's just like at the end, when you reach to C, you should see a 0 or you should see a 1 to a stop, right? So I can write that down using, in this way, that from C over a transition of 0 or 1, you go to a state which is an accepting state. And that's going to be the only accepting state that we have. Okay? So one thing here is that from data accepting state, you cannot actually go anywhere else. So that is the end of the string, in fact. I have written more clean solution for you here. So here I'm going to finish the discussion about the introduction of the context-free grammars. I have written more exercises here for you. Try to do them. I have written the solution at the end of the slide. So we are done with chapter 5. You can read all of the sections and probably except the section which is about YAC 5.3.2 that you needed for doing your project. And please do the exercises. If you had any question, we can discuss about that in class or during the office hours.